Okay, so in this section we'll consider some of the basic requirements of memory management, and we'll make a few observations that hopefully we can keep in mind when we actually start to consider mechanisms that allow for memory management. So I guess the first thing to do is to think about maybe some of the general requirements, the principles, the needs that processes have, and that the operating system must attend to. So we've already made previously a distinction between the idea of a program and the idea of a process. So a program is a much more nebulous and vague concept because it might refer to the source code that the programmer creates. It might refer to an executable file that's stored somewhere in the file system. It's vague, so the key thing is that when we're talking about processes, well, we mean a very specific thing, and that's a program which is loaded into main memory and which is ready to execute, where execution means the fetching, decoding and executing of its machine code instructions. So the first point is that for a process to be able to execute, it has to be in main memory, and that's a fundamental requirement of any computer system. A secondary requirement is that the memory space that belongs to each process must be protected. So we can't have a memory management system that allows a process to get access to the allocated memory space of another process. And the reasons for that are to do just, I suppose, with fundamental considerations of security and privacy. If you can access a process's address space, then you can see its data structures, you can see its variables, and that's not great from a privacy point of view. And if you can see it and you can also change it, then obviously that could be abused for malicious purposes. Likewise, the third point there is also very, very important. The operating system, and by that we mean the kernel, well, its address space must also be protected. If it's not protected and ordinary processes can see and also access the memory space of the kernel, then effectively what you have is the subversion and compromise of the most important entity in the system, because one of the key features of the kernel is that it's privileged. It has absolute control over all software on the system, and it has absolute control over all hardware. So if you are a bad actor and you're wanting to compromise a system, then the first thing that you would look to do is to access the address space of the kernel. So the address space belonging to the kernel must be protected. Another point is that the user process must be unaware of memory management. So we'll really talk about this in a later lecture, which is about virtual memory. But remember that we started this lecture and we said, well, the user process operates in the little bubble of delusion, which says that it has absolute and total access to all the memory in the system. So the perspective of the user process is very simple. It believes that it is the only process executing in the computer, even though that's not true. And then our final point is one that I think we made earlier on. We'll look at different memory management techniques and we'll see what their flaws were, and once we understand what their flaws were, we'll then review paging. And once we have an insight into paging, that'll be very helpful, because that is the real system that is used by real computers. We can also add a little bit as well about programs. So one of the things that we know about programs is that they exist as a file on disk, and then for them to be transformed from a program, from an executable file, they have to be loaded into main memory, and they have to be transformed so that they become a process, and when they are a process, their machine code instructions can be fetched, decoded and executed. Now what we also have to observe is that a process may not stay in main memory all the way through its entire lifetime. So we'll talk later on about the idea of swapping processes out, although that's not a major consideration. And what we'll also note as well is that addresses, references to locations in main memory, can be represented in a number of different ways. So we can consider them as being symbolic. So for example, we might talk about variables declared in a program, and we might say, okay, there's a variable int count, or there's a string employee first name, and they are conveniences that allow programmers to think more easily about the problem space that they're trying to resolve. But in reality, what they have to refer to, these symbolic variable names, is to addresses in memory. Another way to think about addresses is in terms of their number values. So we might say that such and such an address is 15 bytes or 110 bytes from the beginning of a portion of main memory, and we'll see that as a concept later on. And then also as well, we can think about addresses inside an address space as being absolute. So one thing to think about is that an address space is a portion of main memory, or even main memory itself, which starts with address 0 and then continues 1, 2, 3, 4, 5, 6 to wherever the end of that address space is. So in the example that we've got here, you can see that we've got an absolute address, which is 174,044. So that's an absolute address. We have a little bit here which we don't need to worry about too much, which is about mapping from one address space to another. So we'll talk about this in a little bit more detail, which is the idea that there's a logical address space for a process, and then there's the physical address space. Now, the logical address space and the physical address space are not the same. Now, if we go back to this diagram here, I drew your attention to the fact that these numbers here, these addresses, were the actual addresses that were being referenced by this program as it executes. But when we think about that physical referencing, we'll realise that in a multitasking system that will not work. Okay, so we talk about the binding of logical addresses to physical addresses. Now, in these bullet points here, we're just talking about when that can be achieved. So all we need to know is that the binding of logical addresses to physical addresses can be done when the program is first loaded into main memory, at the point at which it becomes a process. That's the second point. And it can also be done during the execution of the process. So we'll see that later on. The first option here is not really an option unless we were considering a very, very simple computer like the one that we saw earlier in the lecture. Okay. Now, this diagram is an interesting diagram because it captures some of the issues that arise. So what the diagram tries to represent is a main memory inside a computer, and you can see that there is a kernel. You can see that there is 3 processes, P7, P22 and P12, and you can see that they have been allocated portions of main memory. So this is of course very unrealistic, but we'll not let that stop us, and we'll say to ourselves, okay, what is the range of addresses that are occupied by the kernel? And we can see that is from 0 through to 300, or 0 probably through to 299. We can see that P7 occupies a range of addresses which go from 300 through to 499. We can see that P22 executes in an address space which is 500 through to 699, and then finally P12 executes in an address space which is from 700 through to 900. Now you can see the CPU over here just for the sake of context, and I guess then the question is, well, is this realistic? And there are 2 problems with it, of course. So it's not realistic at all. The memory is tiny. That's one aspect of its lack of realism, and we can see that the addresses that we've got here, they are physical addresses. They're actual hardware addresses. So what's the problem with this setup here? Well, you can see that our problem arises with P7 executing the machine code instruction LOD 101, and that I guess, illustrates what the problem is. LOD 101, LOD is a machine code instruction which stands for load direct, and 101 is referring to a memory address. Now, you'll remember that in an earlier slide we said that it's a violation of memory management policy to allow one process to access either the kernel's address space or to access the address space of another process. So we can see that the obvious problem that arises here is that when P7 executes LOD 101 and 101 is referring to a physical address, then we can see that essentially what P7 is trying to do is it's trying to execute an address space that belongs to the kernel. Now that's absolutely not on. We require the kernel's address space to be absolutely private, and we also require it not to be alterable by any other process that's executing in the system. Because remember, the kernel is privileged, and these processes up here, they're very much restricted in terms of what they're allowed to do. So what we have to be able to do is to translate this address, which cannot be a physical address, into something that is meaningful. So what do we mean by being meaningful? Well, we mean that the 101, 101 is actually an address space that is an address space that belongs to P7. So I think we could offer up the idea that the logical address 101 has to be mapped to an address range, a range of physical addresses which is between 300 and 500. And likewise, when P22 executes LOD 101, it isn't referring to the physical address 101 down here. It has to be referring to an address which exists in the range of physical addresses that have been allocated to P22. So 101 has to be mapped to a physical address which is somewhere between 500 and 699. And then finally, when P12 executes the machine code instruction LOD 101, the 101 of course is not referring to the physical address 101 down here. The logical address 101 is in fact referring to an address that exists somewhere in the portion of physical memory that has been allocated to P12. So this 101 has to be mapped to an address that is in this range here. So how is that done? Well, we'll see that in a minute, but I'll tell you now that 101 will be mapped to the physical address 400 when it's executed by process P7. I'll tell you that when P22 executes the machine code instruction LOD 101, that the logical address 101 will be mapped to the physical address 600, which will be about here. And I'll tell you that when P12 executes LOD 101, that the logical address 101 will be mapped to the physical address 800, which is roughly about here. Okay, so that's one problem that arises with this very simplistic model of memory management. But there's a second problem, which is that these processes are using up all of the available physical memory in this very, very simple computer that we're looking at here. So what happens if, for example, P7 decides that it needs more memory? So let's imagine that P7 opens up a file and it needs to process the contents of that file. How will it grow its portion of physical memory? So you can see that there's no spare memory in this model here, and consequently our processes do not have the capacity to grow. So that also is a problem.